Yeah, okay, so I thought actually what I wanted to start with is to fill in some of the references from last time and try to give some pointers to the literature. And then I want to today start talking about the paper by Badmore and Schatzer. But maybe first we'll wanted to review some of the history for THH and so forth. So THH and the description of THH of FP. So this description of THH of FP is really what starts everything off. Which even in this spot more Schultz stuff, this is really sort of the basic calculation that makes everything work. So this is due to Buxted in unpublished work. As I said last time, but I should also say that it was equivalently done by Breen. It's also done by Breen in a different form. In the language of functor homology. So it was also done by Breen purely algebraically. But I think one of the things that you really need to get to get this theory off the work, to get this theory off the ground, is that you need the multiplicative structure on THH of FP. But still, so it seems that to get THH of FP as a ring, so the homotopy groups of THH of FP as a ring, one needs some topological input, such as the dual Steenrod algebra, some spectral sequences, and so forth. Some topological input, e.g. Steenrod operations, and so forth. But I just wanted to note that this, at least additively, this calculation can also be done. Yes.
Sorry. Yeah. It seems your iPad lost connection.
Oh, sorry. So I think someone just tried to call me, which might be why.
Oh, okay.
Sorry.
Can you reset it up?
Is it okay?
Yeah. Now it's working.
Right. Thanks. Okay. So yeah. So it seems that at least to get it as a ring, you need some topological input like Steenrod operations. But I just wanted to mention that there are sort of purely algebraic approaches to computing THH of FP, at least additively, using things like functor homology. So there's a paper by Franju, Lan, and Schwartz that also explains some of this and gives a purely algebraic description of the calculation additively. But you do need the multiplicative structure for this. So for a reference, since Buxted's paper is unpublished, so for a reference for this THH of FP, this topological calculation, there's the paper by Blumberg, Cohen, and Schlickl, which explains how you use the fact that you compute THH of FP using the fact that FP is a Thom spectrum. So that's a result of Hopkins and Mahold. And so you can use that to compute THH of FP. Okay. There's also, So also a very general, and so this actually applies to everything that I want to say, but so there's a nice reference for a nice discussion of this as well in the notes by Krauss and Nikolaus. So see also the notes by Krauss and Nikolaus. So this is available. I think it's available on Nikolaus's website for a discussion, for a detailed discussion, especially of the multiplicative issue. Okay. So notes, and these are notes on topological on THH, and topological cyclic homology, cyclotomic spectra, and so forth. And I should just mention that there's a lot of really valuable material in this space. We recommend that. Okay, so that's part of it. So next, I just wanted to give the references for topological cyclic homology. So the construction of topological cyclic homology. So topological cyclic homology appeared in work by Buxted, Shang, and Madsen. So they construct topological cyclic homology of a ring and the cyclotomic trace map from the K-theory of a ring to the topological cyclic homology of the ring. And they show that you can use this. You can use the fact that you have this map, and you can use the fact that you can control topological cyclic homology to say things about algebraic K-theory. So I think their applications were towards assembly maps in the K-theory of group rings. That was the original application. But so after that, there was a theorem of Dundas, Goodwillie, and McCarthy. So after that, there was that. So the connection between K-theory and topological cyclic homology was sort of made tighter by the theorem, which I alluded to last time, of Dundas, Goodwillie, and McCarthy, which states that if you have a ring R, so if R is a ring, and I is a nilpotent ideal, then so in general, it's not true that K-theory and topological cyclic homology are the same, but it is true that their variation along a nilpotent ideal is the same. So you have a Cartesian square involving the K-theory of R, topological cyclic homology of R, K-theory of R mod I, and topological cyclic homology of R mod I. So that's a homotopy Cartesian square. And what that's saying is, well, if you know the K-theory of R mod I, then to figure out the K-theory of R, you have to do a topological cyclic homology calculation. So for example, you know the K-theory of FP, then if you want to calculate the K-theory of the dual numbers, you have to do a topological cyclic homology calculation, basically. And often this is more doable. So this is the theorem of Dundas, Goodwillie, and McCarthy, which came after that. And this theorem has a lot of applications to computing K-theory. So I think so a lot of this work was done by Hesse, Holt, and Madsen. So applications by Hesse, Holt, and Madsen. To compute K-theory of lots of rings. So maybe one of the famous ones was computing the algebraic K-theory of local fields. And the idea is that you reduce everything to the K-theory of finite fields plus some topological cyclic homology calculation. So, so I'm talking about references. Let me just mention that there's a nice survey by Madsen. So see Madsen's survey, algebraic K-theory and traces. So I guess he talks a lot about cyclotomic spectra, topological cyclic homology, and then explains some of these applications to K-theory as well. So there's a nice long survey by Madsen that explains a lot of these ideas. Okay, so that's topological cyclic homology. Next, I want to say something about cyclotomic spectra. So cyclotomic spectra. So the definition of topological cyclic homology came well before one really had a homotopy theory of cyclotomic spectra. So originally, the idea is that the symmetry that THH of a ring has the symmetry of a cyclotomic spectra, and when you take that into account, that gives you topological cyclic homology, and you can express that using the formula TC of R. So I should say something about cyclotomic spectra. So you can express that using the formula that TC of a ring R is Homs in the category of cyclotomic spectra from the tensor unit in the category of cyclotomic spectra into THH of R. So that's so classically maybe originally, like in Buckshot, Chang, and Madsen's paper, one didn't have this category of cyclotomic spectra. So initially, one didn't have cyclotomic spectra as a homotopy theory. So one can actually, so this formula wouldn't actually be meaningful, and instead one defined a topological cyclic homology using an explicit construction. So instead defined TC defined sort of more explicitly. So in fact, this is raised. So this question of actually defining the category of cyclotomic spectra so that you can make, for example, a formula like this true, is mentioned. This question is mentioned by Colliden in his 2010 ICM talk. And Crillon considered, so Crillon did consider the version of this when you work Z-linearly. So if you, not cyclotomic spectra, but modules over the integers. So fine, but the category of cyclotomic spectra as a homotopy theory was written down by Blumberg and Mendel. So it's constructed, sorry, let's say the homotopy theory of cyclotomic spectra was constructed by Blumberg and Mendel. And it does make the above, and so then once that's constructed, then the formula for topological cyclic homology is true, and formula above is correct. So one can identify that, they identified that with the classical formula for topological cyclic homology. So then after that, this category was also described by other authors. So it's also this homotopy theory of cyclotomic spectra was also described after that by Barwick and Glassman, and also by Ayala. Oops. Sorry. Oh. Oops. Sorry. Let's say that again. Ayala, Meselji, and Rosenbaum. So using so maybe translating it from the language of genuine equivariant homotopy theory into, for example, a language in terms of spectral Mackey functors. So there are various ways you can present this category, and so it's also described in these other papers. And then I guess recently the work by Nicolas and Scholze showed that in all these descriptions, there's actually a simplification that happens. So Nicolas and Scholze show that all of these descriptions of the category of cyclotomic spectra actually contain some redundancy if you're working in the bounded below case. So all these descriptions of cyclotomic spectra have a fair bit of redundancy in the bounded below case, which is the case that is relevant for this discussion. And I guess they observed that essentially what happens is that the certain Tate spectra automatically vanish in this bounded below case. So they prove something they call the Tate orbit lemma, which shows that some of this gluing data that you have to write down, that in principle you have to write down, is just canonically zero. So they give the description. So they give the definition of the cyclotomic spectrum. So they give. And so they use that to give a description of the category of cyclotomic spectra, taking into account this simplification. So in particular, that's a description that I was discussing last time. So in other words, it's a spectrum X with a circle action and this Frobenius map from X to its CP-Tate construction, which is appropriately S1 equivariant. Equivariant for the identification between S1 and S1 CP. So that's based on this observation. And so I also the description of the descriptions. So that's their description of cyclotomic spectra, and also the description of topological Hochschild homology of the commutative ring that I discussed last time also appears in there. So the description of THH of R for our commutative ring is from that paper. And then finally, I want to mention a very recent, just from last month, work by Antio and Nicolas, which gives yet another, a very different description of cyclotomic spectra, which also relies on this vanishing of Tate constructions observed by Nicolas and Scholze. And they give yet another description of cyclotomic spectra, which actually looks quite different. So they give a description of cyclotomic spectra of the category of the homotopy theory of cyclotomic spectra in terms of their TR. So in terms of the invariant of the invariant, the classical invariant TR. And it's well, their description of cyclotomic spectra is called topological Cartier modules. So they show that a cyclotomic spectrum, again, with these boundedness conditions, is equivalent to giving a spectrum with certain operators that kind of look like the operators that you see on a Dieudonné module, which shows up when you try to describe like p-divisible groups or finite group schemes. So there's also a very new description of cyclotomic spectra in these terms, and it's actually a description in terms of the invariant TR. Okay, so that's some of the literature on the subject from last time. So sorry not to spell this out this time. Okay. And also, I guess maybe once again, I also just want to recommend the notes by Krause and Nicholas for a discussion of some of these points. Okay, so in the remaining two lectures, I guess I wanted to explain some aspects of the work of Botner and Schulze, which relates topological Huxell homology and related invariants to p-adic homology theories. So let me just sort of state the main theorem that I want to try to explain. So main theorem, right, so main theorem. So all of this is due to Botner and Schulze. Is that if R is a smooth algebra over a perfect field, so if R is a smooth over a perfect field K, which is characteristic P, then there is a filtration on the invariant, well, so let's call it TP of R. And by definition, that's THH of R that is a circle action, and you take the S1 Tate construction. So take the S1 Tate construction on THH of R, that's something you can do for any ring, even a non-commutative ring. And then the statement is that if you have a smooth algebra over a perfect field, then this invariant has a filtration whose associated graded is two periodic, so it's two periodic crystalline cohomology of R. So maybe just sort of the most sort of basic case, what if R is FP? So if R is FP, well, so the idea of crystalline cohomology is that crystalline cohomology is an integral version of Durand cohomology. And so if R is FP, well, the key thing that happens is, well, we saw last time, so THH of R, so THH of FP, on homotopy groups, that's given by FP bracket sigma for sigma an element in degree 2. So that's Sohbats theorem. And this, so remember last time that this is sort of one of the benefits of working with topological Huxell homology as opposed to ordinary Huxell homology, that you get this polynomial, right? And then TP of FP, which is the S1 Tate construction. Well, you compute it using the S1 Tate spectral sequence. And when you write down the S1 Tate spectral sequence, there's just no room for differentials because you have something which is even degrees. So THH of FP is in even degrees. And when you take the S1 Tate construction, there's just no room for differentials. But there is room for extensions. And in fact, I guess what you have to verify is that the extensions are as non-trivial as possible. So you get that TP of FP, well, it's ZP brackets, let's say X plus or minus 1, where X is in degree minus 2. So X is the class that comes from the cohomology of CP infinity. Yeah. Right. Okay, right. So in this case, well, the crystalline cohomology of FP is just ZP. And so of course that's what we're seeing at the level of homotopy groups. In this case, the filtration is just the Poisson filtration. But so notice here that I just wanted to make the point that it's sort of important that you consider topological periodic homology, because it's an invariant which starts with, you're feeding into it an FP algebra, something in characteristic P, and THH of FP is still something in characteristic P. But what's sort of remarkable is that when you take the S1 Tate construction, well, P is 0 in THH of FP, but it's not S1 equivariantly 0. So when you take S1 constructions, you actually get something which which is an integral, which is over ZP rather than over FP. And the claim is that it actually, it recovers crystalline cohomology. Okay, so maybe let me make one more remark about this idea. This idea of providing a lift. So another remark, so this is also due to BMS, is that if R is any FP algebra, then when you consider TP of R, so actually R doesn't even have to be commutative here, so it could be non-commutative, then TP of R is a module over TP of FP, which is this two-periodic ZP. And the observation is that TP of R, when you base change from ZP, so derive base change from ZP to FP, so then this is canonically HP of R relative to FP. This is another way of thinking about what this construction TP of R is doing. So TP of R is this S1 Tate construction on THH of R, and it's, according to BMS, it's something which on associated gradients is crystalline cohomology. But there's a statement that you can make very generally, which is that whenever you have an FP algebra, possibly non-commutative, then TP of R is an integral lift of periodic cyclic homology. So it's and if you think of periodic cyclic homology as being something that should be related to de Rham cohomology, then maybe this is this is already suggesting that you're sort of looking in the right direction. So you can think of TP as some sort of non-commutative version of crystalline cohomology, and when you have a commutative ring, when you have a commutative FP algebra, then it has a filtration whose associated gradient is literally crystalline cohomology. Okay. Right. So there's a general procedure. So constructing this filtration seems to be a bit of a subtle operation. So constructing this filtration seems to be somewhat subtle. So by the way, I should mention that now Antio and Nikolaus, in the paper that I referenced, have given a construction of this filtration. Have actually have reproved this in sort of a very elementary fashion, have reproved in a simpler fashion. But, sorry, so they gave a simpler construction recently. But I guess part of what's important for this construction is, what's important for BMS is that if you run the same types of constructions, you can also do it in a mixed characteristic. So BMS, what they really want to do with this is that they want to build new p-adic homology theories. So they really want to input mixed characteristic rings. They really want mixed characteristic rings, e.g. ZP, instead of FP algebras. And the cohomology theories that you're going to get are going to be quite a bit more complicated and subtle than crystalline cohomology. So I guess what I wanted to explain for the rest of these lectures was just the characteristic P case, just to make things simple. But what happens is that their methods of constructing this filtration work, more or less the same in characteristic P or in mixed characteristic. Yeah. Okay. So how to construct these types of filtrations? So how to construct on TP of R? Well, it's sort of two steps. So R is a smooth FP algebra. So for the purposes of my talks, R is a smooth FP algebra. But the idea is, well, step one, you're going to derive your functors. So even though you're only interested in smooth FP algebras, you're going to derive functors appropriately. So derive all functors, let's say derive all functors, so can apply them on arbitrary FP algebras, in particular large FP algebras. I'll say what large means in a little bit. Well, TP of R doesn't really need any deriving. TP of R is already something that makes sense for any ring. But we'll have to talk about things like the cotangent complex and derive de Rham cohomology. So we'll have to derive. So when I say derive all functors, I mean really derive differential forms and de Rham cohomology. Okay, so somehow first you want to prove something with smooth algebras, but you actually want to define your construction on all algebras and actually apply it to algebras which are very much non-smooth. You want to apply it to some huge algebras, and then you want to do some sort of descent. So then construct the filtration on TP of R directly for these large FP algebras. So I'll say what large means in more detail, but roughly it's regular semi-perfects. So these are going to be very non-Noetherian FP algebras where the Frobenius is surjective. And there you just you just compute what TP is directly, and the filtration is just a Postnikov filtration. So the idea is that, well, first you derive all your functors so that you can apply them to arbitrary FP algebras. And then you construct your filtration and prove the theorem, not for smooth FP algebras, but for these regular semi-perfect algebras. And you might ask, like, why would you want to do that? But the reason is that everything is much simpler for these large algebras, because for these large algebras, TP is in even degrees. So the key thing that happens for these large FP algebras is that TP is in even degrees. And that makes it a lot easier to define the filtration. It's just a Postnikov filtration. And then you define the filtration for smooth algebras by phase-free flat descent. So here there's actually a theorem that you have to prove that these invariants are going to satisfy phase-free flat descent. So that's a rough sketch of how you construct this. So I thought I would start with saying some things about construction one, this derived functor construction. So derived functors. And then maybe I should say non-abelian derived functors. And this is sort of a very general construction. I think it goes back in some forms to Jordan-Pupa, to Crillon, and many others. So the construction is the following. So let me explain, for example, how you take derived functors. Well, so for example, it's familiar how you take derived functors in the sense of like Tor and ext and so forth. But it's also possible to take derived functors of non-additive functors. So let's talk about example. So maybe I'll just illustrate this with some examples. We have, let's say we're working over a field K. And well, we have the symmetric power functor, let's say sim I, from vector spaces over K to vector spaces over K. So it turns out this functor admits a derived functor. Which now is going to go, so let's call this, I'll just still call this sim I. To be really clear, I could write an L here, which is going to go from the connective derived category of K to the connective derived category of K. So the connective derived category of K means you're considering chain complexes of K modules up to quasi-isomorphism, and connective means that there's no homology in negative degrees. And so the claim is that this admits a canonical derived functor. And what this functor is doing is explicitly, given a chain complex P bullet, well, you apply Dold-Kahn to turn it into a simplicial K vector space. Right, so sorry, so the reason why this is sort of a little bit tricky is that if you have an additive functor, you can derive it by just applying it to a chain complex, and you get a chain complex. But now you have to be a little bit careful because you have some sort of non-additive functor. But the idea is that you can do it for simplicial objects. So explicitly, the idea is that given a chain complex P bullet, you use Dold-Kahn to turn this into a simplicial K vector. Oops. Simplicial K vector space. So I don't know, let's call that P prime bullet, but now bullet means simplicial rather than complex. And now if you have a simplicial object, you can apply any functor to it. So just consider sim I of P prime bullet as a new simplicial vector space. And now apply Doldcon again. So I guess previously we were really applying the inverse of Doldcon to get a chain complex. And so this is the derived functor of the symmetric power. So I guess something that one has to show is that this doesn't depend on p-bullet up to quasi-isomorphism. So this is a construction, well, this is a construction that's turning a chain complex into a simplicial vector space, applying sim I simplically, and then applying Doldcon again. And so I guess something that one checks is that this is really a functor on the derived category. So this is something that you can do. Oops, sorry, at a level of the derived category. Okay, so the next example of this, so you can define derived functors of symmetric powers, exterior powers. Really, anytime you have a functor from vector spaces to vector spaces, you can use this to define a derived functor on the connective derived category just by taking simplicial resolutions. Okay, but so the idea of simplicial resolutions is pretty general, and it's going to work in other settings. So another setting is a setting of the Crillon cotangent complex, and in particular, you can do this even when your starting category is not that. So this is the setting of the Crillon cotangent complex. So again, let's fix a base field K. And the idea is that we're going to consider the category of commutative K algebras. So for every commutative K algebra R, we can associate to this the modulo of 1 forms omega 1 of R over K. So this is the modulo of Kähler differentials. And the idea is that we want to take the derived functor of this construction. So Kähler differentials. And well, the cotangent complex is the derived functor of this construction. So the derived functor is the cotangent complex. L of R over K. And what you do is the following. So the construction is as follows. So let's say R is a ring. So then you choose a simplicial resolution of R by polynomial K algebras. So if R is any K algebra, choose a simplicial K algebra, commutative K algebra P bullet, with an augmentation from P bullet to R, which is a quasi-isomorphism. So you choose a simplicial resolution of R by polynomial K algebras, and then the cotangent complex of R over K is, well, you have a simplicial polynomial ring P bullet. So you take 1 forms on the polynomial ring, on the polynomial rings Pi's, and take differential forms on them over K, and then take the geometric realization. So in other words, omega of P bullet over K is a simplicial object in K vector spaces, and you take its geometric realization. So that's a cotangent complex of R over K. Right. So more generally, this is going to make sense if R is not just a ring, but a simplicial ring. So R can be a simplicial commutative. And you can do this construction by choosing a simplicial resolution by simplicial polynomial rings. So the key property of this construction is that, well, in general, if you take this complex in degree 0, its homology of R over K is just the same as ordinary differential forms of R over K. But in general, there can be higher terms. So it can be higher homology. But it does not happen if R is smooth over K. Well, sort of tautologically, if you take R to be a polynomial ring, then that polynomial ring is itself a simplicial resolution by polynomial rings. So for a polynomial ring, the cotangent complex is just differential forms. But then there's something a bit stronger that one proves, which is that for a smooth algebra over K, this cotangent complex is just computing differential forms. So you can say this type of construction a little bit more axiomatically as follows. So you can state this construction axiomatically as follows. So consider the homotopy theory of simplicial commutative rings. Okay. And so let's consider it as an infinity category. Well, simplicial commutative rings, this contains as a full subcategory the category of finitely generated polynomial rings over K. So you have simplicial commutative K algebras, and that contains finitely generated polynomial rings over K. So now then the fact is that if C is any infinity category with sifted colimits, so that means it has filtered colimits and geometric realizations, then there's an equivalence between functors from just polynomial rings, finitely generated polynomial rings into C, and functors from all simplicial commutative rings into C. And I say functors prime, meaning commute with sifted colimits. So it's something very formal. It's saying that if you want to, this is just sort of how you define these derived functors in general. So you have some sort of invariant of rings, and what you do is you restrict to polynomial rings, you restrict to finitely generated polynomial rings over K, and then that canonically extends in a unique fashion to all simplicial commutative rings if you demand that it commutes with sifted colimits. And what that construction is doing is literally take a simplicial commutative ring, pick a simplicial polynomial resolution of that, and then apply your functor simplicial-wise to the simplicial polynomial resolution. So this is sort of a general axiomatic way of expressing this construction. And for example, what we're doing here is we're taking C to be, let's say, derived category of K, and the functor F to be differential forms on polynomial rings. And then you use this equivalence. This equivalence is a form of Kahn extension to define it on all simplicial commutative rings. So this is sort of a general fact that's making this work. By the way, there's also an analog of this type of universal property for derived symmetric powers. So instead of taking simplicial commutative rings, you could instead formulate a similar universal property for the derived category. So this is right. So this is a general construction, but maybe just one thing that's worth keeping in mind is this is always something you can write down. So if you have something on rings, you can just restrict to polynomial rings and then extend to all simplicial commutative rings, and then you have a derived functor. But I guess what this construction is not in general telling you is it's not telling you how to actually compute it. So in general, you don't know anything. It's hard to make this explicit. It's pretty hard to make this explicit. Well, by construction, it's hard to make this derived functor construction explicit on rings which are not polynomial rings. So, so what this construction is doing is it's a derived functor of an original functor, and there's nothing derived happening on polynomial rings. On polynomial rings is just the original functor, but well, polynomial rings are kind of special, and what you might hope is that you can actually control this derived functor on a wider class of rings. So in general, that's a theorem. That type of statement is a theorem that one has to prove. And so an example of such a statement is that the Crillon cotangent complex L of R over K is actually just the same thing as differential forms on R over K. Well, certainly if R is polynomial, sort of tautologically. More generally, if R is okay. So now I want to give another example of this beyond the cotangent complex. And that example is important for this discussion of topological Hochschild topology. And that's the example of derived Durand cohomology. So what is this construction? Well, let's recall. So again, K is a base field. That if R over K is an algebra, and really maybe we should say smooth, let's say smooth for simplicity, then we can consider that the Durand complex, omega of R over K bullet with the Durand differential. So this is a commutative DGA over K. Right. So that's the algebraic Durand complex, which we can write down for a smooth algebra over K. And so I think very start of these lectures I was talking about that. So let's say that's a construction from smooth algebras over K into some category. And well, I could say, I don't want to say chain complexes because I want a category, where I can really talk about geometric realizations and so forth. So for example, we can consider this as a functor from smooth algebras over K to E infinity algebras over K. That's a construction that sends R to omega of R over K with the Durand differential. So we have this construction, and while we were just talking about derived functors, so this construction right now, I only really want to think about it on smooth algebras because, well, differential forms are maybe not so nice. Maybe you don't want to think about differential forms on non-smooth things. You only want to think about the derived version anyway. So let's say we try to derive this construction. So I think also this was first done by Ilusi. So what this is doing is, well, first restrict to polynomial rings. So let's recall what this is doing. First restrict to polynomial rings. And then resolve all rings, or all simplicial commutative rings, by polynomial rings. So then you get a functor, which I'll call dr over K, which is going to go from simplicial commutative rings over K to E infinity algebras over K. And this is so-called derived Durand cohomology. And explicitly what it's doing is, if R is a polynomial ring over K, it's just the usual Durand complex. And in general, it's based on some resolution. So this turns out actually to be a little bit tricky. So I think Ilusi did not quite consider this. Ilusi considered a completed version of this. And it was actually a fairly recent observation of Bott, so theorem by Bott, which is that if K is a perfect field of characteristic P, then this derived Durand cohomology of R over K agrees with ordinary Durand cohomology of R over K if R is smooth. So this is another sort of really key observation in getting some of this theory started. So in general, you can always derive your functors. You can derive any functor you want, but you may not have any hope of actually being able to control it except on polynomial rings. But obviously you don't want to just consider polynomial rings for geometric applications. Maybe you want to consider smooth algebras. But maybe a priori it's going to be really badly behaved even for like K brackets X plus or minus 1. So Sohbats theorem is that this derived Durand cohomology construction in characteristic P, and it's really specific to characteristic P, does recover the ordinary Durand complex for a smooth algebra. So this is sort of a pretty crucial point, and it's not true in characteristic 0. In fact, in characteristic 0, in characteristic 0, de Rham cohomology of polynomial rings is contractible because the affine line is contractible. So derived de Rham cohomology of any ring is just k in degree 0. So derived de Rham cohomology is not very interesting in characteristic 0. And it was a recent theorem of Bott that if you have a perfect field in characteristic P, derived de Rham cohomology in characteristic P actually gives you the thing that you want. So we'll also say that this relies on, right, so this really relies on the fact that you're in characteristic P, and it relies on the Cartier isomorphism and it's called conjugate filtration. Okay, so this is an example where you can really control the derived functor on something larger than just rings, or so just polynomial rings. Okay. So there's also a similar analog of derived crystalline cohomology. Oops. Sorry, I need to charge my pencil. But so maybe I'll just say this in words because it's formally analogous. So you have a notion of derived de Rham cohomology, which deriving de Rham cohomology, and you can also do this for crystalline cohomology. You consider crystalline cohomology for polynomial rings, and then conextend to all rings. And then for a similar reason, I guess corollary of Bott's theorem is that again for smooth algebras, this recovers. There's no higher derived functors on smooth algebras. So there's also a theory of derived crystalline cohomology. So it agrees with ordinary crystalline cohomology on smooth algebras. Okay. So so maybe in the rest of the time today, what I want to explain is how you can use this machinery of derived functors and so forth that I've just been discussing to make a pretty concrete statement about Hochschild homology. So what I want to do is I want to explain the following proposition. I want to apply this discussion to Hochschild homology. I want to prove the following proposition. So let's say K is a base field. Let's say R over K is an algebra, not necessarily smooth. Then the claim is that the Hochschild homology, Hochschild complex of R over K, has a descending filtration. Or I should say maybe it's a convergent descending filtration, whose associated graded. So GER I is given by the derived ith wedge power over R of the cotangent complex of R over K. So just to be very clear, the Hochschild complex of R over K, this is some, say it's a simplicial commutative ring. In particular, it's an object of the derived category of R, derived category of K. And we're saying that it has a filtration whose associated graded, well, it's the ith wedge power over R, and this is already a derived functor. This is a derived functor in the sense of deriving exterior powers of the cotangent complex of R over K, which is also a derived functor, derived functor of differential forms. And so maybe just to be very precise, what I really need to do is I need to consider, so the cotangent complex of R over K is actually an R module. It's actually in the derived category of the ring R, not just in the derived category of K. So I guess I glossed over this point a little bit earlier. And the wedge power, wedge I, is the ith exterior power in R modules, is the derived ith exterior power in the category of R modules. Okay. So I hope that's clear. So proof, actually this is very formal. So this is maybe the first type of filtration that we want to think about. So the idea is that we want to think about Hochschild homology and THH and TP and so forth by filtering them by things that are easier to control. And something that turns out to be easier to control is the cotangent complex for various reasons. And so maybe the first theorem that you prove, or the proposition you prove in this business, is that Hochschild homology has a filtration in terms of wedge powers of the cotangent complex. And actually, this is not so hard once you have this machinery of derived functors. So what's the proof? Well, let's consider this invariant. So consider the functor Hochschild complex of R over K from the category of simplicial commutative K algebras to, again, let's say the derived category of K. So let's consider that as a functor. We can do that. And let's observe that this functor commutes with sifted colimits. So abstractly, this functor, this commutes with sifted colimits. And the reason is that, well, the Hochschild complex is built up from the Hochschild complex of a ring R or simplicial commutative ring R, is built up from various tensor powers of the ring R. And all of those constructions commute with sifted colimits, so this construction does as well. Okay, so in particular, this construction, so by what I wrote down earlier, everything is determined whenever you have a functor on simplicial commutative rings, which commutes with sifted colimits, everything is determined by what happens on polynomial rings. So everything is sort of just formally determined by taking simplicial resolutions by the values on polynomial rings. So in particular, if you want to define what Hochschild homology is, and furthermore, if you want to define what this filtration is, it really just suffices to do it on polynomial rings. So in fact, the construction of Hochschild homology over K is completely determined by its value on polynomial rings. Right, but if P is a polynomial ring, then we have the HKR theorem. So the HKR theorem states that the Hochschild homology groups of P over K, so for P a polynomial ring, are given by differential forms on P over K. It's given by the algebra of differential forms on P over K. That's the HKR theorem. In fact, HKR is, well, maybe this is sort of a trend now. It's true for polynomial rings, but it's actually, well, it's true for smooth algebras. So true for smooth algebras more generally. And now, well, that's great because we can just take the Pahasnikov filtration on the Hochschild complex of P over K. So take the Pahasnikov filtration. So let's call this Fi of HH P over K is just ith connective cover of Hochschild complex of P over K. And if you take the Pahasnikov filtration, then whoops, sorry, when I stated the theorem, I stated it wrong. I should have a shift by I here. So first take the ith wedge power of the cotangent complex, and then you shift it by I. Sorry, it's a mistake. Right, so you take the Pahasnikov filtration, and the associated graded is just the homotopy groups. So associated graded is the homotopy groups, and the homotopy groups are HKR. They're given by ith wedge power of omega of P over K. And then since that's in degree I, we have to shift it by I. So in particular, we've proved the proposition if P is a polynomial, right? And now you sort of formally extend. So prove the proposition if P is polynomial. And now you essentially con-extend. So now resolve anything by simplicial polynomial rings. Now extend formally by con-extension, simplicial resolution, to get the statement in general. And that's a proof. Okay. So this proposition is a very formal statement somehow. Just because everything is commuting with sifted colimits in a sense. But in order for it to be useful, we need, in order for such a result to be useful, what we really need is we need examples of rings for which we know the cotangent complex. So for this to be useful, need examples of rings, well, other than polynomial rings, which are tautological, for which we know the cotangent complex. And okay, well, we said we know the cotangent complex well for smooth algebras, it's just differential forms, but we need some other examples. And let me just give one maybe to wrap up today, and it's the following example. So proposition. So let's say K is a perfect field, P. And let's say R over K is a perfect ring. It's a perfect ring, meaning that the Frobenius map from R to R is an isomorphism. Right. So then the statement is that the cotangent complex of R over K is just contractible. So perfect rings are very much not smooth. They're not at all smooth. They're non-Noetherian. They can be quite messy. So perfect ring is one where the Frobenius is an isomorphism, and maybe I should just give an example. So example is take Fp, add a variable x, and add all the p power roots of it. Sorry. So this is a perfect ring. It's a union of polynomial rings in the variables x to the 1 over p to the n. And then the statement is that if you have such a perfect ring, the cotangent complex is just 0. It's completely 0. And the reason for this, well, the idea is that, well, let's prove it on differential forms. The idea is that in degree 0, it's just differential forms. So in degree 0, or in H0, we're seeing differential forms on R over K, 1 forms. And we need to show that dx equals 0 for x and R. But x is equal to y to the p, because Frobenius is an isomorphism. So dx equals d of y to the p, which is p times y to the p minus 1 dy, which is 0 because we're in characteristic. So there's no differentials, and you can upgrade this argument to show that the whole cotangent complex vanishes if you have a perfect ring. And by the way, I think there's no analog of this in characteristic 0. In characteristic P, you have this large class of rings. For example, rings like this perfect polynomial ring, where there's just no differential forms. I don't think there's any analog of that in characteristic 0. Okay, so right. So corollary, we end with this corollary. If R over K, so if R over K is a perfect ring, then the Hochschild complex of R over K is just in degree 0. The Hochschild homology of R is just in degree 0. And what's the proof? Well, use the filtration from the previous proposition. So maybe we should call this the HKR filtration. And the HKR filtration is saying that the Hochschild complex is filtered by exterior powers of the cotangent complex of R over K, but that cotangent complex is just 0. So the only thing that contributes to the filtration is just R in degree 0, and so you get this statement. So another consequence that you can get from this, so maybe I should stop. But another consequence is that topological Hochschild homology of R, if R is perfect, then topological Hochschild homology of R is R bracket sigma. So I said that last time for a perfect, for FP, and it's not hard to extend it to perfect fields. And this is saying it's actually true for any perfect ring, not necessarily a field. And so that's going to be really crucial. So the fact that it's true for perfect rings, which are not necessarily fields, is going to be crucial in actually setting up this BMS filtration. Okay, so I think we'll stop here and we'll continue next time. Thanks.
Okay, I'll mute everyone. Let's thank Akhil. So, any questions? If there are any questions for Akhil?
question.
Yeah, go ahead.
Akhil, maybe you already said this, I don't know. You explained what the S1 tape construction, or rather the homotopy groups of the S1 tape construction of topological Hochschild homology of FP was. And is there a similar simple description if you look at homotopy fixed points rather than tape construction?
Yeah. So sorry. So the question is, can you describe? The question is to describe the S1 homotopy fixed points of the ring THH of FP. And the answer is, it's the following. So on homotopy groups, it's the ring generated by two classes x, sigma, modulo the relation x times sigma equals p, where here the degree of sigma is 2. So sigma is a lift of the class in THH of FP, the Boxstead generator, and the degree of x is -2. X is coming from the cohomology of CP infinity. It's coming from the fact that you have S1 homotopy fixed points. So you get these two classes, sigma and x, and their product is p. So this is the description of the ring. When you form the S1 tape construction, then you're inverting x. So then you don't need sigma anymore. So more generally, So more generally, there's a description of this. This is going to work for any perfect ring where you would replace ZP by the Witt vectors of that perfect ring. So let me just also mention that a very nice source for this is the paper by Nicolas and Schulze, where they describe THH of FP as a spectrum. They completely describe THH of FP as a cyclotomic spectrum. And in particular, one of the nice things that they show is that as a spectrum, THH of FP, when you can, the homotopy groups are given by Boxstead, but you can describe the whole spectrum, and it's precisely the connective cover of take ZP, take the CP tape construction of that CP acting trivially, and take the connective cover. So as an E infinity ring spectrum, you have this description. And so you can use this to see, to see all of these formulas.
Great, thank you.
Any more questions? If there are no more questions, I'll unmute everyone and let's thank Akhil one more time. And we'll continue on Thursday.
On Thursday, so either I'll catch it in an airport or I will look at it late, but nobody should look for me.
Akhil, thanks for the flexibility to do this one in your home.
Wait, sorry?
Yeah, thanks for your flexibility to do this one in your home. Yeah.
Oh yeah, thanks. Yeah.
Very good. Yeah, thank you.
Yeah, this is a lot smoother. Yeah. Sorry. Yeah. Sorry about the issue. Yeah. The office Wi-Fi.
Yeah, thank you.
Yeah. Thanks for hosting today.